Thank you very much. Bear with me. This is my first talk in the new era in person. And, you know, I know you guys here have been staring out at the ocean, and this is what it looks like looking west from LBL half the time. So this is you can't see, but the Bay Bridge is out here somewhere. So this nice view from Berkeley. Okay. I'm just gonna jump right in, not a lot of introduction. What's our main goal? So first of all, I'll say I've designed this talk assuming most of you don't know Lattice QCD in as much detail as I do, but you might have some understanding of numerical analysis. So what do we want to do? What's our goal? We want to have a theoretical prediction of neutrino nucleus cross-sections from the standard model with full uncertainty quantification. I don't mean completely systematic like in an effective field theory sense, but we want uncertainty quantification as people who have to model systems talk about uncertainty quantification at least. You know, one motivation, of course, is this Dune accelerator, which is going to resurrect the dinosaurs. So somebody from Dune put this up on April 1st, like 5 years ago, and I found it, and it's hard to find this one anymore, but I found this in time before it got taken down. So why do we want a theory prediction from the standard model? Well, the analogy is not perfect. Here, this analogy I'm talking about. If you haven't read this book, it's a fun read. This is Carlo Rubio was so sure he was going to get a Nobel Prize for discovering supersymmetry. He hired a journalist to follow him around and document the discovery of supersymmetry, which would lead to his Nobel Prize. And as we know, it turned out this was really just QCD jets. There wasn't supersymmetric particles. And so the point, if we want to look for new physics, we better be pretty darn confident we understand the background. In this case, that's QCD. So if we really need to know how to predict to the best of our ability nuclear neutrino cross-sections from the standard model. Of course, that's impossible. I wrote very challenging, but I'll just say in words, it's probably impossible to have a real standard model prediction. It's certainly impossible to have a unified theoretical description across the entire energy range of interest. We know the neutrino beam goes up to several GeV, and that moves from the region where effective field theory makes sense into a region where we don't have any real control, like there's a bunch of Reggie stuff happening at this energy. You know, Reggie's a model, can't say it's QCD. And then if you go to very asymptotically high Q squared, of course, you have deep inelastic scattering, you have perturbative QCD. You can do lattice QCD for single nucleon physics. You can talk about the resonance region with lattice QCD. So you can start by looking at the delta contribution to N to delta, pion production. There's new ideas floating around to get the inclusive N to everything cross-section. Those haven't been fully worked out yet. But those are the kind of things you can do. That's single nucleon. We know what we're really thinking about as a nucleus, not a nucleon. You can use effective field theory to describe the low energy region, so low energies and also low Q squared. And by low, I mean, you know, well below 1. So that's interesting for T2K, but for Dune, I don't know how interesting that is. Rigorous effective field theories have a hard time getting above carbon 12, and you put them into these quantum Monte Carlo methods. So we have to figure out how to get to nuclei as big as argon. We don't know how to do that yet rigorously. And again, we can do deep and elastic with lattice QCD. There's all this parton distribution function work going on. So that's great. But what we really want is a description of medium-sized nuclei over a broad energy range. We have to think about pion production, resonance, final state interactions, and a whole lot of stuff that's very, very challenging theoretically. Okay, and here's a plot from Calum sitting in the audience here. Okay, so what can we do? So first of all, just to tell you, I optimistically describe myself as a realist. So maybe some people will call me pessimistic or conservative. So I'm not going to give you a flashy, glowing, we can solve everything point of view. I'm going to say, well, we can work really hard and we can do a couple things that are important, but we're not going to get super far with lattice QCD. So we can do quasi-elastic scattering, of course, no problem. We can already go up to about almost 2 GeV squared. There's techniques to take us up to 5 GeV squared that people are working on. I'm quite confident we'll get the resonance region down. We can do pion production. We can do 2 pion production, that kind of stuff. Deep and elastic. We can start to look at 2 nucleon cross sections. So that's sort of like in the next 5 years, I think you'll start to see rigorous 2 nucleon cross section calculations. Maybe we can do light nuclear cross sections directly with lattice QCD. So if I was wildly dreaming, I'd say maybe you can get up to an A equals 5 system in the post-exascale computing era. Maybe. And then even if somehow magically someone figured out how to calculate the neutrino carbon-12 cross-section, almost assuredly that would not be the most economical way to try to propagate QCD theory into the description of a nuclear neutrino cross-section. So again, no effective field theory can describe this over the whole range of energy we're interested in. But what we can at least do, this is where some of the uncertainty quantification comes in. We can use effective field theory with lattice QCD input to describe a region of the parameter space that we can control rigorously with systematically improvable uncertainties. And then what you can do is you can take your model of the nuclear cross-section, and with this you can reach up into, say, carbon-12. Then you can take your many-body nuclear model and you can calibrate it in the region where you have systematically controllable uncertainties to at least constrain what kind of uncertainties will come up in the nuclear modeling that you have to do. Okay. So what can we do now? So single nucleon charges, so the scalar charge, tensor charge, axial charge, we can do those at the percent to few percent level. So here's just a plot from the flag, the lattice averaging group, looking at the GA, which is of course related to neutrino cross sections at zero momentum transfer. And you can see there's this nice precise determination of GA. Interestingly, it turns out it was believed previously that the QED corrections to GA were sub-percent, and we didn't need to worry about them. But working with some nice effective field theory people, and this guy Leendert Hand, who's sort of a mix of a theorist and experimentalist, we realized, in fact, there are percent level QED corrections to GA. So you can think of them as pionic structure corrections to the nucleon. In fact, so these weren't estimated in the dispersive methods or the current algebra methods. And so, you know, whether they're a percent or not, we don't know because there's some low energy constant that's unknown. We have to pin that down. So you actually have to use lattice QCD to take advantage of the precision. You have to add QED to lattice QCD to take advantage of the precision in the purely isospin symmetric QCD calculation to actually compare this number to experiment. So right now, there's a roughly 2% uncertainty on relating experimentally measured GA to the QCD isospin symmetric predicted value of GA. That's kind of cool. Or, I don't know. I thought it was cool. Maybe not everybody has that opinion. You can control specific flavor decomposition. So for example, one of our organizers is very familiar with this work because she's on the papers. You can look at the up, down, strange, charm cross sections separate. So if you have a current going into up, down, strange, and charm, we can separate those out in QCD with lattice QCD. So we can say specific statements about isoscalar, isovector, if you want. I think for most neutrino stuff, we care about the charge current cross section. The quasi-elastic form factors, like I said, now reach up to the maybe 2 GeV squared. There's a few groups who are working on this. 2 of them have done a very exhaustive job, and the rest of us are kind of catching up. There's investigations of higher momentum. I call it still kind of the R&D stage because we haven't seen these methods take off yet. There's not a lot of results coming out. Not to say that the method itself needs research and development, but maybe how much computer time you have to invest in it. What's the best strategy? This is kind of work that's ongoing. There's very preliminary 2 nucleon matrix element calculations going on with lattice QCD. I'd say that a huge caveat here is these were all calculated with a method that had some assumptions that we now seem to believe means those results are just wrong in an uncontrollable way. So we're now coming back in to try to fix this. They've all been done very far from the physical biomass, so there's no rigorous connection to the physical biomass. They've mostly been done with a single lattice spacing. There's a whole huge host of systematics that have to be brought under control, but people are actually working on this, building into 2 nucleon corrections. Okay, so rest of the talk. I'm going to give you a flash introduction to lattice QCD. I'm going to share with you, attempt to share with you why the calculations are difficult, just to give you a feeling for why we don't have the answers yet that you may want. I'll show some single nucleon quasi-elastic results, talk about the phenomenological impact, and then where are we going from here. Now, I have tried to actually keep this talk at 30 minutes because we're told to be 30 plus 15. So let's see how well I do. So here's QCD. What do? We're going to compute a correlation function. We create stuff out of the vacuum at time 0. We annihilate it at time t. We write down the path integral formulation of this, and we say, this is a big integral. We don't know how to do this integral. Okay. We do know how to integrate the quarks exactly, so we can play a trick and get the determinants, because it's a Gaussian integral. We know QCD is quadratic in the quark fields. But if we stick it in a finite volume, at least we turn this infinite dimensional integral into a finite dimensional integral. Then what do? You've seen this picture many times. We stick the gluons on the links. We stick the quarks on the sites. And this is a technique to preserve the gauge invariance of QCD when you discretize the theory. And we know gauge invariance is very important for gauge theories. Then you say, well, I still don't know how to do the integral. So let me go to Euclidean space-time. And then suddenly, I can interpret this as a probability because at 0 chemical potential, this is just a real number bounded between 0 and 1. And so I can do a probabilistic Monte Carlo estimate of the integral, set up a Markov chain, and then I can approximate the correlation function. I can do a finite number of background gauge fields, the gluon fields, weighted by this determinant of the quarks and the action of the glue. And then I have a rigorous prediction, which has errors that scale like 1 over the square root of n. This is just statistics. So a lot of people think, well, can't you just calculate this with QCD? And of course, as you all know, Lattice QCD is not an app you can download on your phone and just get answers out. Maybe in 20 years we can do that, but not now. And also a key thing I want to stress, what we're computing is the Euclidean space finite volume correlation function. We're not even directly computing the observable we want. We're computing correlation functions which contain the observable we want, but we still have to tease that observable out of the correlation function. And that's non-trivial. So there's a lot of sophisticated data analysis, at least for theorist standards, to extract the spectrum, matrix elements, form factors. And as soon as you start talking about multi-particle initial or final states, you have some very technical formalism you have to understand how to implement. You can think of it as, an infinite volume. You have a continuous distribution of momentum. You have an infinite Fock space. If you go to finite volume, you have a finite periodic Fock space in your theory. And there's some mapping of how do these continuous states map onto the discrete states. And there's some power law volume corrections, and there's some complex formalism you have to understand to do that. Okay, and then once you've done that, well, what do you have to do to get a real answer? Okay, you have to go to the continuum limit, and this means you need at least 3 lattice spacings. Why 3? Because we know you can draw a line between any 2 points. We have to be able to differentiate between a straight line and a curve to know if we're really entering what we call the asymptotic region, which means we understand rigorously how the discretization effects are vanishing and going to 0. And this computational cost scales roughly like the inverse lattice spacing to the 6th power. So if you want to take the lattice spacing in half, you have a factor of 64 more compute you need to get the same answer. You have to take the infinite volume limit. This isn't too bad. In fact, we don't want to take it too big most of the time because we take advantage of the finite volume to get information about the spectrum. And the real killer for nuclear physics applications is going to the physical biomass. You encounter this exponentially bad signal to noise problem. And this is the biggest prohibitor for why lattice QCD hasn't done more for nuclear physics. So here's just an alternative explanation for the sign problem. Not the sign problem, the signal to noise problem, which is very related to the sign problem, which I picked up chatting with David Kaplan in the halls back at the University of Washington. So if you think about it, the building blocks of QCD are quarks, but the eigenstates of QCD are hadrons. They're made out of the quarks. So when you do a lattice QCD calculation of a quark, that must carry the eigen information for all the states in the spectrum. We know the pion is much lighter than the nucleon. So the eigenvalues of the pion, which behave exponentially in the long time limit, like roughly half the pion mass, you get a third of the nucleon. So all this information is contained in a quark propagator, and the pionic degrees of freedom contribute much more to the quark than the nucleonic degrees of freedom. And so if you make a pion, that's easy. You just tie them together and you get something that behaves as you expect, like the pion. But when you want to make a nucleon, what you have to do is add 3 quarks together and cancel all the large pion degrees of freedom out of the thing you're computing to extract the much smaller nucleonic quantity. And so if you've ever added big numbers and tried to subtract them to get a small number, you're just going to have a numerical challenge doing that. That's basically the signal to noise problem in an alternative way of thinking about it. Okay, so here's a quick derivation of a correlation function, just assuming you don't do this on a daily basis. So we have a creation operator again. Now I've put it at space location 0 times 0. I destroy it at some space location x times t. I give it some momentum. If I just focus on 0 momentum, so we have what we call a mixed time momentum correlation function. That's what we typically calculate in lattice QCD. The first thing I'm going to do is I'm going to time evolve my operator. So remember, I'm Euclidean space, so the time evolution has this e to the minus ht, e to the ht. If I define the vacuum that has 0 energy, I can ignore the action of the Hamiltonian on the vacuum. That just gives me 0. I'm going to multiply by 1, because in theory, we learned you either multiply by 1 or add 0. That's how you solve every problem. And then you multiply by 1, you apply the Hamiltonian, and you get this energy E on the state N. And then once you focus on the 0 momentum, you project out only the states. So here, this is a sum over all states in QCD, but I've done a 0 momentum projection, so I only get the 0 momentum states. And then we get this nice sum of exponentials. So this is the God-given theoretical model for the correlation function. There's no approximation at all. The only approximation comes in when you fit to a finite number of exponentials, because we know the tower is infinite. We have a discrete finite information, so we have to make a truncation model of how many states we're going to try to fit. And if you've tried to fit noisy exponentials, this is also an ill-posed problem. This is one of the classic, very challenging problems to do in data analysis. Okay. If you wait a long time, well, first, this expression is true for every time. I can just pull out the ground state, and I get 1 plus the sum of corrections, or here I'm defining this delta n0 is just the difference between the nth energy and the ground state energy. So here I'm using omega for my vacuum, because I write 0 for the ground state, because I think in C or Python, where your iterator starts at 0, not at 1, like in Mathematica. And then we always construct what we call these effective masses, which is just take the correlator, divide it by itself at some shifted time, take the log of that, and we see in the long time limit, this just gives us the energy. So we talk about these plateaus. All we're doing is we're looking at effective mass. We're looking for when the sum of this extra stuff becomes small, we can identify the ground state energy. And if you happen to use the same operator to destroy the state that's conjugate to the creation operator, you can actually show all these R's have to be positive definite. This makes life easy. The systematics come from one direction, easy to fit. Well, okay, it's not so easy to fit. So here is an example of an omega baryon correlator. A physical pion mass is a lattice spacing of 0.09 Fermi, a pion mass of 135 MeV. What are you looking at? You're looking at the data, the numerical data are these dots with uncertainties on them. The bands are a posterior reconstruction of the effective mass after I've done the fit. And what you can see is if you try to wait a long time where you expect to see the ground state, you can just see the noise, as I was describing before, the signal to noise problem. The noise is growing exponentially. This is a very tough problem to beat. You're not going to beat an exponential with a polynomial increase in computer time. Or if you do, it's a very poor choice of what you've done with your life. But that's what almost all lattice people do because we don't have a lot of better ideas. We're trying to come up with them, but they're hard to come by. And so what you have to do is what I would call some sophisticated analysis, where I want to study the extraction of the ground state energy, which is what these colored dots over on the right are, as a function of all the knobs I might possibly want to change, the number of states I use, the minimum time I use, the maximum time I use, et cetera. And then what you can try to do is come up with some robust uncertainty estimate of your ability to extract the ground state information. So this is the absolute simplest case you can look at for a baryon where we have noise growing as a function of time. On the bottom, so this is a Bayesian analysis as well. So this Q factor is just to make us feel good at, once you have Bayesian analysis, the Q factor or the chi-square per degree of freedom no longer really makes sense because you have to define what do you mean by degrees of freedom. There's no well-defined prescription for how to do that. But still, roughly, well, first of all, it's a number that goes from 0 to 1. And roughly you want it to be higher than lower. So it just gives you some fuzzy, warm feeling of the quality of your fit. When you have a Bayesian analysis, if you have fixed data and all you're doing is changing the model, you can come up with a rigorous answer to the question, which model is most preferred by the data? And that's what this weight factor is here. So they're normalized so that the sum of all the weights goes to 1. For each different time, I have different data. So I can no longer compare easily a fit with different amounts of data. But at least for fixed time, I can come up with a rigorous answer to which model is most preferred by the data. And it's basically doing an Occam's razor type of selection. Okay, 3-point functions. So the most common method that we all use, first of all, it's suboptimal, but it's the most common method because it's so far been the most economical in terms of compute cost and human resource cost, is to compute the matrix elements for a few values of t. So here at t sep, the figure came from an old plot where I called it t sep, and I was too lazy to write sep for every t. So it's t and t, those are the same. Okay. And then what I'm going to do is the way we do the calculation, I can't arbitrarily vary t sep. Well, there's other techniques people do where they can't arbitrarily vary t sep. What most people do, you have to fix t and 0. You have to have a fixed separation of your creation and annihilation operator, because what we do is we solve a quark propagator coming backwards, and then we put in the current. And then the 3-point function has a similar construction as the 2-point function. So what you do is for a few values of t, you compute the 3-point function for all values of the current insertion time. Each choice of t is a new calculation, which brings lots of new numerical cost. Ideally, this t, you'd want to be roughly 2 times the value of t where you think your ground state is dominating the 2-point function. If I can find it. Oh, I lost it. So it would be roughly twice, in this particular case, 25. But because of the signal to noise problem, that's just not going to happen. So the ground state matrix element can only be determined, or the form factor, through an extrapolation in t and tau through this analysis. And this is where actually the analysis becomes much more sophisticated. So here, the 3-point function, I do the same spectral decomposition, multiply by 1, time involved operators. And the 3-point function, here is the information you want. So there's this ground state energy. This is the matrix element you want. So it's 0 momentum. This is just GA if I put an axial current. And then I have this whole tower of excited states I don't want, but I have to deal with them. I've just called them scattering states when the initial and final state are the same state. And if they're different, I call them transition states. The thing to note is the scattering states only depend on this source sink separation time. And the transition states depend on both T and tau. So any curvature you see in this plot here, this is our psychedelic moose plot, all the curvature is completely driven by these transition matrix elements where I change like a nucleon to a nucleon plus a pion. So that's a transition state. Or if I have a nucleon and a pion at momentum 0 back-to-back goes, so nucleon and pion at 1 unit of momentum back-to-back, that's also a transition. And so all this curvature is the transitions. And you'll note, even though the colors are hard to see, for intermediate values of T, you can actually see what looks like very little excited state contamination. And that's, you're being fooled because there's positive and negative contributions coming from excited states. And so we don't have the same monotonic approach to the asymptotic value that we do in the two-point function. So we have to be much more careful. We have signs, opposite sign contributions polluting the correlator we want. This gray band is the value of the matrix element you want. As you can see, there's a non-trivial extrapolation to get there. Okay. So comparing it to the two-point function, so now this is from the same data set. If I look at the largest separation in time, which is roughly 12 units in time, and I look at the two-point function at 6, so this 6 is if I have a source at 0 and I put the current exactly in the middle, that's how far, this is what the two-point function looks like. So you can see there's a very large amount of excited state contamination. And this is why you can also see it's impossible to pull the system so far apart that you can ignore these excited states. And then this is just doing the same thing except at non-zero momentum. At non-zero momentum, the way we do the calculation, most of us, is that we fix the momentum of the sink to 0. We inject some momentum transfer. Momentum conservation then tells us the source has the opposite momentum. And then you see this asymmetry develop into numerical data. But here, what I'm showing you is we put in the theoretical model of what this should behave like. We do some analysis, and then we can reliably describe all of the numerical data. And so we gain confidence that we can extract these matrix elements. And where this becomes extremely challenging is if I want to do this analysis, I have to, if I want to track the correlation, I have to fit all of the data simultaneously. And I get a very, very large amount of numerical data I want to fit with a very large number of parameters to describe this. And you don't have enough data to properly estimate the covariance matrix. So we have a situation where we have extremely highly correlated data where we cannot properly estimate the covariance matrix. And you know that's a very difficult problem to do if you want to do your numerical analysis and extract the matrix elements. So we are learning how to do analysis. So I'd say some lessons learned. You probably were aware that lattice QCD was falling short when we're getting a value of the axial charge. It was like 10% too small for a long time. We're now 99% sure this was excited state contamination was just the driving factor, and we figured this out. And this is to tell you, this is why you should believe our form factor results, because we figured out the problem for GA, and now we're applying all this information when we calculate the form factors. We cannot pull the source and the sink far enough apart to suppress the excited state contamination. It's just numerically not a smart thing to do. So you're stuck having to fit the excited state contamination. You have to have at least 3 values of this source sink separation time, because if you just use this model with one excited state, you have 2 parameters, you better have at least 3 data points to have a 1 degree of freedom fit. That's my statement why we need at least 3. Most groups are taking a strategy where they compute 500,000 to 1 million stochastic samples at larger values of the separation time. Some of us are also advocating for, well, maybe let's use a whole lot of source sink separation times with less statistics to try to do, in my opinion, a better job understanding the systematics of the excited state model you use to describe the numerical data. Okay. And this numerical analysis is critical. Like I said, we have these highly correlated data sets. They're incredibly important also for the form factors. I'm not going to talk about that at all because Sarah's going to talk about this next. There's some interesting things with the PCAC relation. The other thing we know for sure, the operators we are using to create and destroy the states are very suboptimal. They're not, if you could design what you would do, it's not what we are doing. But everything else you would do is so much more expensive numerically and human resource wise that it just hasn't been done much yet. So it's not because we don't know that we should do better, it's just because it's very expensive. And when I say very expensive, I mean you get one of these Insight Awards on the biggest supercomputer in the world, you can do a quarter of what you want to do, right? So you have to apply multiple years in a row to get the time to build up the answers you want. Okay, what should we do? The thing we really need to do is incorporate these variational methods where we don't just use a single operator, but we create a whole set of operators and we do a matrix to matrix correlation function. And then we can try to come up with questions like, what's my optimal nucleon? It's going to be some combination of something that's 3 quarks, which I've labeled a nucleon, plus something that looks like 5 quarks, which is a nucleon and a pion, some linear combination of this stuff. If you think about it for a moment, you'll realize this is a 3 quark object. This is a 5 quark object. The next guy up is going to be a Roper, a 7 quark object. And so if you want to start tying these quark lines together, you develop a very expensive combinatorial problem of trying to tie the quark lines together. So this is what we know we have to do, but it's very expensive. But what you'll get out of it is hopefully you'll be able to remove the n-pi excited state contamination, which will give you the ability to extract your information earlier in time because you're removing the dominant excited states. And early in time, I have better stochastic noise. And so this is kind of like what one of these n-pi operators might look like. And then there's some cool formalism you can understand for when you have multi-particle final state, and you have a resonance, you get some very non-trivial. This is the factor you need to multiply the lattice QCD number to extract the infinite volume quantity you're interested in. So this is not like oh, it's a 5% correction. This is a factor of 50. The lattice QCD number is a factor of 50 different from the infinite volume answer. So this is very important, non-trivial stuff. Okay, I'm getting close to the end. I've already run over my 30 minutes, but I promise you I'm close to the end. So here's some results for the form factor. This is all the groups that have results at the physical pion mass. The bands, the enemy collaboration, I like to, is Rajan Gupta. He and I like to argue a lot, so I get to call him the enemy. This is Regensburg QCD. Sarah's going to talk about this next. I don't know if CLS and mines are actually the same or different. I apologize. Konstantine's going to talk about this later today. CalLat is the group I work with. ETMC, this is Martha and collaborators. PAX-CS, this is our Japanese friends who've made these really huge boxes. It's kind of cool. If there's a band, they've attempted to do the full continuum extrapolation. If there's dots, we haven't done that, so there's some systematic leftover. 1 to 2 years, and we're going to have a fully quantified prediction for the quasi-elastic charged axial form factor. And what I mean by fully quantified is there's going to be 8 groups that are all competing for the best answer, and we're all going to do the full continuum analysis. And so we're all going to be fighting to each other who's the best. And you look at the spread of us, and that will be the QCD prediction for the single nucleon quasi-elastic form factor. So what I'm going to do is I'm going to look at this and say, I know most of us haven't done our systematics, but if you look at the spread in these results, you can see they're done with very different discretization schemes. So these are things where away from the continuum limit, we don't have to agree. In the continuum, we have to agree. They might be different box sizes, etc. The fact that we are all basically lying on top of each other means those systematics most likely are small enough to ignore. And we become more confident in that because the 2 groups who've done the full continuum extrapolation, you know, if I told you that band was fitting this data, you wouldn't tell me that's obviously wrong. So, okay, I'm just going to ignore the fact that most of us haven't done it and say, what if this is the answer from QCD? So I can look at this form factor, and this is a Z expansion parameterization, and then I can compare it to the extraction of the axial form factor from the deuterium bubble chamber data. So this is done by Aaron Meyer. And you can see they don't agree. It's just something's wrong. QCD, as determined from lattice QCD, is wrong, or there's something wrong with the extraction from the experimental data. They can't both be right. We have systematics left over, or we're wrong, or there's something wrong here. If you just take this form factor and then you plug it in to predict the single nucleon cross-section, this is coming from the extractions from experiment and phenomenology, these different bands. This was highlighted as the big tension, these two different extractions. But what you can see is if you just stick in the lattice QCD number, you have a much bigger discrepancy, right? This is a 30% increase in the single nucleon cross-section. And then if you say, well, what if I stick this into Genie? So this was done by Calum sitting here. And you can say, I'm not going to do what I know I should do. I'm just going to keep everything fixed in default Genie, but I'm only going to change the single nucleon form factor and ask how big of a change does that have on the predicted nuclear cross-section. And this is for T2K in the near detector on the left and the far detector on the right. To draw your eye, so this nominal Genie is the black dashed blue line, which is this one sitting in the second highest one. And then if I just simply replace the single nucleon form factor with that coming from lattice QCD, I get this pink band. And that's that 30% increase in the single nucleon quasi-elastic cross-section. And you can see, of course, the normalization is not a constant as a function of energy. That means it's going to be very non-trivial to fix this problem. You can't, there's not a simple fix. You can just wash it away. And the normalization is not the same in the near and the far detector. So you might screw something up in trying to infer something about what's going on in the far detector from the near detector. And then you have the same thing for Dune. So you can see this discrepancy between the nominal and the replace the single nucleon with lattice QCD value. And again, the ratios are not the same. They're energy dependent. This is obviously not what you do. You don't go in and you adjust other things like the two particle, two hole, or the resonance region or something else. You know you have to change something else. But this just shows you if you just take this one piece and replace it with the QCD truth, which has a big quote around it because we don't have our final answer yet, you have a very non-trivial change going on. And you better figure out what, as much as you can, you want to inject the real standard model prediction for this stuff. Go in and replace little pieces at a time as we make progress. Okay, future directions. I've already talked about this. I've talked about this. We have to implement this variational basis. And the first group to really do this correctly is also Sarah, our speaker next. She's involved in this work. And once we do that, in addition to improving the single nucleon calculation, we'll also be able to go for the resonance region and pion production with that same technology. So that's around the corner. That stuff is being developed now. So within 5 years, you're going to see real honest results from this kind of calculation. Just taking a slide from, we're trying to get some money from LBL to pay us to do some work. We being Calum and I. So if you just take what currently goes on look at the resonance region, what's used by almost everybody in these event generators is the original model, the FKR model, which is very unsatisfactory. It has a simplistic description of the neutrino-nucleon interaction. And the authors actually said, our model uses a description that is naive and obviously wrong in its simplicity. And that's from 50 years ago, and we're still using it. So, okay, it's time to upgrade. So we're trying to get some money from LBL to demonstrate what an upgrade might look like. Something else I'm going to mention, sorry, I'm going to waste a couple minutes of your time. The convergence of baryon-chiral perturbation theory. Why do you care? Single nucleon is done at the physical pion mass now. Why do I care? Well, if I want to start looking at two nucleon corrections, those are not going to be done at the physical pion mass for 5 years. I don't know. Maybe within the exascale era, they will. But the point is that means we're going to rely on an extrapolation in the pion mass to extract our answers. But the problem is, if you look at something simple like GA, the series is not converging. So what you see, this is some results I was involved in, very mild pion mass dependence. And then if you look at what's contributing order by order, so first of all, this blue band is the leading order result. The kind of salmon colored band is leading order plus next to leading order. And you see this terrible dive. So the next to leading order correction is becoming very big and negative. And then you go to N2LO and okay, I can fix it to describe the data. Well, let me test the convergence of the theory by adding a higher order correction. Well, that's a 0 degree of freedom fit with the data set used here. And then the problem is you see when I add this next order fit, so this is the full and 3LO chiral perturbation theory prediction, the convergence pattern gets worse. So adding a higher order makes the convergence worse. So my conclusion, not universally shared. Well, so first of all, why do we care again? Because if I can't get the single nucleon effective field theory to converge, why would you believe the two nucleon effective field theory? Because it's the foundation of the two nucleon effective field theory is the single nucleon effective field theory. There's no avoiding that. Okay, so blah, blah, blah. There's other problems. There's this funny linear in the pion mass dependence of the nucleon mass, which is also suggestive that there's strong order by order cancellation. So when you have an expansion that's supposed to be perturbative and the different orders are strongly competing against each other, you probably don't have a good expansion. And just to put numbers on it, if you look at the size of the corrections, N2LO is larger than NLO in the opposite sign. So my conclusion is SU2, baryon chiral perturbation theory, without an explicit delta degree of freedom, is not a well-defined effective field theory because it does not converge. Therefore, you cannot trust results that are used where the extrapolation was done with SU2 baryon chiral perturbation theory. Adding the delta might help because for GA, there's a large NC cancellation between the nucleon pion and the pion delta loops. So it's understood why you suppress the pion mass dependence. But for the nucleon mass, the delta pion virtual loops add coherently with the nucleon pion loops. And so they make the convergence worse. So the nucleon mass is kind of barely converging. And if you add the delta, you might spoil it. You might fix GA and spoil the nucleon mass. So this is something that has to be sorted out, because we're going to have to extrapolate our two nucleon results for quite a while. Okay. And then the two nucleon, well, before you believe anything, we have to resolve this controversy, this decades-old question, is there a bound state at a heavy pion mass or not? It's not an academic question. It's really a question of, are the methods I'm using robust and reliable? If I can't get them to work at an 800 MeV pion mass, you better not believe anything I'm doing close to the physical pion mass, because I have an uncontrolled systematic uncertainty. Okay, some conclusions. Okay, I sound negative. I want to be positive. Like, we can really do something useful with Lattice QCD. We can help the field. I showed you, I think, why. Because this is a problem. If you inject QCD and you change the problem or your prediction, that's a problem. But we can actually come in and help. We can slowly pick apart pieces and add more and more rigorous contributions from QCD to the modeling of these event generators. Sorry, the modeling the event generators are used to do. The event generators I don't think are modeled, right? All right, okay. Lattice QCD is not a black box. We have to do some very sophisticated data analysis. In 1 to 2 years, we'll give you the robust prediction from QCD of the axial form factor of the nucleon. In the near horizon, we're going to really start going after the resonance region, pion production, two nucleon charge form factors, etc. And then what we can do is we can couple these into effective field theories of nuclear physics, which can then be tied into the many-body nuclear problem and integrated into the event generators. And thank you.
Let's say, you saturated the time.
So I took all my time, I'm sorry.
No, it's fine. The flow of the ideas was perfect. We have time for one question, and then we will discuss it in the afternoon.
Well, if you were to compare two nucleon calculations versus resonance calculations, it sounds to me from what you described that the transition form factors are next, right? Whereas the two nucleon currents seem to be much more complicated and uncertain. Did I understand your message correctly?
Probably. So let me confuse it. In some respect, the two nucleon calculation is in principle easier because I don't need disconnected quark loops. So if I do a pion production, I have to have a quark line that goes from the source to the source or the sink to the sink to make a pion. And previously, I would have told you I thought the two nucleon would come first because that extra disconnected loop adds more noise, more computational challenges. But then this controversy in the two nucleon system says, wait a second, I don't know if anything I'm doing is correct. And now I have this convergence problem with EFT. So probably, yes, the pion production and resonance stuff will be what's reliable sooner. But I wouldn't make a confident statement that's definitely true, because we think we know how to solve the two nucleon problem now, and it's a matter of sort of turning the crank and demonstrating that it's working. So it could be you see two nucleon results at 200 MeV pion mass in the next year or two, not with a continuum extrapolation, but neither will the pion production or resonance have a continuum extrapolation. So they could be coming out comparably in terms of time.
Don't you have the noise to worry about with all the pions that you can make out of the two nucleons?
Yeah, the noise is worse.
Well, I don't know. I mean, we'll see what you guys tell us, but that was my reading of your talk.
It's probably the right reading.
Okay.
Yeah. I just don't want to make that. Yes, I'm definitely that's going to happen.
Thank you so much, Andre.